In this video, we're going to be looking at an introduction to Newton's laws of motion. There's going to be three key laws. Some of them are things that you have heard before, but we really need to understand these in detail. These are one of the key principles in introductory physics. And so first, a little bit of a historical background. It's important to address these because some of these ideas still come up in everyday thinking. And so the ancient Greeks started to try and understand motion and started to try and describe how things moved. And so Aristotle was one of the first natural philosophers. And he started making observations of things that happened around him. He started to realize that things followed certain patterns. So that was kind of the birth of science. They started recognizing this, and this was referred to as natural philosophy. And Aristotle believed that all objects had a natural place. That natural place was being at rest. And he said that the tendency of an object was to reside in its natural place. So all objects want to be at rest, is what Aristotle thought. Aristotle was also one of the first people to start putting things in categories. He started breaking things up and saying that some objects were earth or water, air or fire. This is kind of the very, very basic idea that led to starting to talk about the elements, and now it's the periodic table of elements that you look at in chemistry. But this was the first startings of classifying things. And so Aristotle said that natural motion of an object happened when an object was seeking to return to its natural place after being moved from that natural place by some type of violent motion. So something ripped the object out of being at rest. And then the object slows down and stops and returns to its natural place. So the natural state of an object was to be at rest in its natural place. And he said if you want to keep an object moving, you need to have a force that keeps acting on it. So once you push on the object, you can make it move, but once you stop pushing on the object, it slows down and stops. And Aristotle was on the right track, but he was not correct. That last statement, that to keep an object moving would require a force, is wrong. There are some people that might be saying, well, no, that's definitely true. If I push on a book and I stop pushing on it, it slows down and stops. And we need to see what Aristotle was missing. There was a big leap that happened from Aristotle and his thinking, and then 1500 years later with Galileo and Newton. And so Aristotle's views remained widely supported until the 1500s, when Galileo Galilei popularized experimentation. He started looking at the motion of objects, and he started really doing controlled experiments, things where you would look at the effects of changing a situation and how that change affected things, and trying to then predict other things. And so one of the things that he noticed is if you push on an object and you let it go, it eventually stops. But he noticed if you push it across rough ground and you let it go, it stopped very quickly. And if you push it across smooth ground, it goes farther. And if you had a very smooth surface, when you give it the same push, it goes even farther. And if you had a really smooth surface like ice, and you give it a push, it goes and it goes farther. And so he started to recognize that the smoother the surface was, the farther the object would go. And so he said, well, I wonder what would happen if I had a perfectly smooth surface. Now, it's not something that he could actually test. But he said, you know, it looks like the smoother the surface is, the farther and farther this object goes. And so if I were to have a perfectly smooth surface where nothing was going on, nothing was interacting with the object, if I gave it a push and I let it go, if it was a perfectly smooth surface, that object would keep going forever. Galileo, unlike Aristotle, recognized that there was something happening. There was some type of interaction between the ground and the object sliding along the ground. We now know, you have all heard of friction, and so we now understand what that is. But that was a great leap to come up with that idea, to recognize that when you slide an object across the ground, it stops not because you stopped pushing on it, but because friction is pushing on it, slowing it down and stopping it. And so after Galileo, Isaac Newton came along, and he built upon the ideas of Galileo, tied them together with other things, and so he came up with this idea of inertia. He said that the tendency of an object is to maintain its current state of motion. Notice that's the exact opposite of what Aristotle said. Aristotle said that if you push on an object, once you stop pushing, it wants to slow down and stop. Isaac Newton says that if an object is moving, it wants to maintain its current state of motion. The tendency of the object is to maintain its current state of motion. If it doesn't maintain its current state of motion, that means that something else had to be acting on it to make its motion change. That's the subtle difference between Aristotle and Newton. And it's very small, but it is extremely important. And so in this chapter, we're starting to focus on Newtonian mechanics. Specifically, we're looking at dynamics. Again, dynamics is the study of why objects move the way they do. So previously we had been talking about kinematics. Kinematics was just describing the motion of objects. We described the acceleration of an object. We described how its velocity changed, what its velocity was. We calculated its velocity at different times. But we didn't really talk about why the object accelerated. So dynamics is the study of why objects move the way they do. If it accelerates, why does it accelerate? If it moves at a constant velocity, why does that happen? What's not happening that causes it to keep moving at a constant velocity? So Newtonian mechanics is based on the laws presented by Isaac Newton. Newtonian mechanics are extremely useful, but they're not perfect. In the past 150 to 200 years, there have been small revisions to Newtonian mechanics. And the two main revisions happen either when you're looking at very large speeds. So in Newtonian mechanics, we're going to look at things like a car driving along, a rocket ship moving, but we're going to look at things that are moving very slow compared to the speed of light. At very large speeds, Newtonian mechanics breaks down and you have to look at Einstein's special theory of relativity. We're not going to be doing that in here, but that's where Newtonian mechanics breaks down. And sometimes people say, well then, if Newtonian mechanics isn't perfect, why bother looking at it at all? And the reason is, it works very, very well for objects that are not moving at large speeds. And to treat a car driving along at a velocity of 20 meters per second and to start looking at things using relativity, that would be like trying to break an egg, not by just tapping it, but by taking a sledgehammer and just banging it and smashing it. The other spot that Newtonian mechanics breaks down is on the atomic scale, if we look at things that are very small. So things that are 10 to the negative 10 meters, or 10 to the negative 9 meters. Things on the atomic scale. And that's when we have to look at quantum mechanics. That was stuff that started to come up in the early 1900s. Again, we're not going to be dealing with that in here, but Newtonian mechanics does break down at large speeds and very, very tiny objects. Okay, so we need to define a few things. The first thing we need to define is inertia. Inertia is probably a word that you've heard before, but in physics, inertia means the tendency of an object to resist any changes in its motion. So a change in motion of an object, that's referring specifically to an acceleration. So a change in motion would be changing the velocity, changing how fast it's moving, or changing what direction it's traveling. And if you change the velocity, you're making an object accelerate. Inertia is a property of an object. All objects have inertia. All objects have a tendency to resist changes in their motion. And so that property of an object does not depend on where the object is located. If I take an object to the middle of outer space, it still has inertia. One of the things that we're going to get into is we're going to get into the difference between the idea of weight, which is the gravitational force acting on an object, and the measure of inertia, which we're going to see in a second is the mass of an object. If I take something in the middle of outer space, it still has exactly the same amount of inertia. The inertia has nothing to do with a gravitational pull acting on an object. It's a property of the object itself. And the thing about the object that gives rise to its inertia is its mass. The mass is a measure of how much stuff is there. That's a kind of a loose definition, but sometimes it's a definition that you'll see. But mass, which is measured in kilograms, this might be different than what you've seen before. Sometimes in chemistry you measure mass in grams. In here, in the SI system of units, we use kilograms. So mass is a measure of how much inertia an object has. The more mass it has, the more inertia it has. And so to see this, imagine that I have a box full of feathers and a box full of bricks. And I go up and I try and make those move. I go up and I kick the two boxes, exactly the same. I go up and I kick the box full of feathers and it goes flying across the room. It was very easy to make it change its motion. It did not have very much inertia. But when I go up and I kick the box full of bricks, I break my foot. And that's because the box full of bricks has much more mass. It has much more resistance to changes in motion. It's much harder to make it go from rest to moving. And again, that kick that I applied to it, that is a force. So a force is what causes changes in motion. A force is a push or a pull that acts on an object. So if you want an object to change its motion, you need to apply a force to the object. Again, how much mass the object has, that is going to determine how easy it will be for that force to make it change. If something has a lot of mass, a certain force will give it a small acceleration. But if it has a very small mass, that same force acting on that small mass will give it a much larger acceleration. But again, the mass of an object, that's a property of the object. It depends on how many atoms you have. If you take a baseball and you find its mass on Earth, and then I take it to the moon and I find the mass of the object on the moon, the mass is exactly identical. If it has a mass of 0.5 kilograms on Earth, it has a mass of 0.5 kilograms on the moon. It still has the exact same number of atoms. Each of those atoms has a specific mass to them. So if you count up the mass of all the atoms and add them together, that is the total mass of the object. If I take it to the middle of outer space, far away from everything, it still has a mass of 0.5 kilograms. That's what we mean when we say that it doesn't depend on the position or location of an object. Newton's first law is something that you've often heard. Newton's first law often will get repeated as an object at rest stays at rest, and an object in motion will continue in motion. But that's not exactly a complete definition. If you look at what's on the screen, it says that an object at rest will remain at rest, and an object in motion will continue in motion at a constant speed in a straight line unless it's acted upon by a non-zero net force. So there's actually two pieces to that. It says an object at rest will remain at rest unless there's a non-zero net force acting on it, or unless there's an unbalanced force that acts on it. There's more force pushing one way than there is another way. And an object in motion will continue in motion at a constant speed in a straight line. Constant speed, moving in a straight line, not changing direction, that's a constant velocity. And an object will continue in motion at a constant velocity unless there's an unbalanced net force or total force. So this is that idea of the book sliding across the ground. The fact that it slows down and stops, that says, oh, there must have been a non-zero net force. There must have been an unbalanced force. That was the force of friction. The force of friction was unbalanced. If I wanted to keep it moving, I did have to keep pushing on it, but not because a push is needed to keep an object moving in general, but there a push is needed to balance out the force of friction. And so together the forces balance out, and then it will continue moving at a constant velocity. I think this way of stating Newton's first law, even though it's more common, it is also a little bit more difficult to understand. A much simpler way of saying Newton's first law, and this is referred to as the law of inertia. Again, inertia is the tendency to resist changes in motion. This first law is saying an object resists changes in motion. It will not change its motion unless there's an unbalanced force. So the simpler way of saying it is just that. The velocity of an object is constant unless acted upon by an unbalanced force. And that actually has both pieces in it. An object that's at rest, that's a velocity of 0. So an object at rest has a velocity of 0. It stays at a velocity of 0 unless there's an unbalanced force that acts on it. And an object in motion will continue in motion at a constant velocity unless there's an unbalanced force acting on it. And so this animation shows Newton's first law in action. If you're driving along and you don't wear a seatbelt, and you're driving at 80 kilometers per hour and you crash into a wall, you are in motion. You will continue in motion unless there's an unbalanced force acting on you. If there's no seatbelt, there's no unbalanced force to cause you to slow down. So you continue moving and you fly out of the car or you fly through the windshield. You keep moving until you run into something that exerts a force on you to slow you down and stop you. If you wear a seatbelt, that seatbelt provides an unbalanced force that keeps you slowing down with the car, and it keeps you safe. It keeps you from flying through the windshield. But this is what inertia is. Inertia is the tendency of an object to maintain its state of motion. So the person is moving, and he continues moving until an unbalanced force acts on him. The mass of an object, we've said this already, it's a characteristic that relates a force to the acceleration. Now what we mean by that, mass measures inertia. Inertia is resistance to changes in motion. And we said that force causes changes in motion. Those were the three things that were on that previous slide. And so we said that changes in motion, that was acceleration. So the mass relates the force to the acceleration. The more inertia something has, the harder it is to change its motion with a certain force. The smaller the mass it has, the less inertia it has, the easier it is to change its motion with the exact same force acting on it. Newton's second law is the mathematical one of Newton's laws. Newton's second law says that the net force acting on an object, the net force means the total force acting on an object, that equals the mass of the object times the acceleration of the object. So the net force is the product of the mass and the acceleration. We get this from the fact that the acceleration of the object is going to be proportional to the force. If I apply a bigger force to the same object, it's going to give it a bigger acceleration. So if I double the force, it doubles the acceleration. But I also get that acceleration is inversely proportional to the mass. If I double the mass, if I have the same force acting on it, it's going to have half of the acceleration. The more massive it is, the smaller the acceleration is for the same force. And so putting those two things together, we have that the acceleration is proportional to F over m. And if we have things in the correct units, so force is going to be measured in newtons, mass will be measured in kilograms, and acceleration will be measured in meters per second squared. If we have things in the correct units, we have that the net force, the total force, equals the mass of the object times the acceleration of the object. Again, net force means the total force. That's all the forces added together. So remember, forces are vectors, so you have to add up all of the force vectors to find the total force vector, what one single force is equivalent to all of the forces put together. This is a vector equation, so this can be looked at in three separate pieces. The x component of the net force is what causes the x component of the acceleration. The y component of the net force is what causes the y component of the acceleration. And the z component of the net force causes the z component of the acceleration. This is something we saw when we looked at projectile motion. In projectile motion, the only force acting was the force of gravity. The force of gravity acts straight down in the negative y direction. So since there was no force in the x direction, the acceleration in the x direction was 0. And because there was a net force in the negative y direction, there was an acceleration in the negative y direction. This equation with the arrow above it, that says that the net force vector equals the mass times the acceleration vector. This says that the net force vector and the acceleration vector always point in exactly the same direction. It's that net force that causes the acceleration. They always must point in the same direction. Again, looking at each of the components separately, that component of the acceleration along a specific axis is caused by the net force along that axis. The acceleration in the x direction is caused by the total force in the x direction only. The acceleration in the y direction is caused by the y component, the y total force only. When we go to look at problems, we're going to look at something called a free body diagram. And a free body diagram is a drawing showing all of the forces acting on an object. So we draw the object, or we represent the object as a dot if we want to make things simpler, and we draw each force on the object as a vector arrow with the tail of the arrow on the object. So let's look at a book sliding across the ground with friction. And so for simplicity, we're going to represent the book with a dot. Again, you could draw the book itself, that's a very simple object, but we could just represent the object with a dot. And we have this book and it's sliding to the right. We're going to see that if it's sliding to the right, that's going to mean that the friction acts opposite the direction it's sliding. So a free body diagram, we draw the individual forces. So we're going to see that we're going to have a force of friction acting on the object. So we draw that arrow, we draw the tail of the arrow on the object. That shows that this force vector is acting to the left. And then as it slides across the ground pushes up on the object. And so we have that force of the ground pushing up on the object, so we draw that vector with the tail on the object. And then we have the force of gravity, the weight of the object, which we're going to talk about in later notes. We have that force of gravity pulling down on the object. So we draw a free body diagram to really simplify things so we can see what forces are acting, what directions are they acting, and we can then look at the situation and see, do any forces balance? So that means that in that direction there's going to be no acceleration. In my drawing, the force of the ground and the force of gravity balance, so that means that object is not going to be moving up or down. This is sliding horizontally across the ground, and so since there's no motion in the y direction, the forces in the y direction will balance. And then we have friction, and because the force of friction is acting opposite the velocity, this is going to have an acceleration opposite the velocity. That means that the object is going to be slowing down and eventually stopping. This sample problem is going to show how to apply Newton's second law and calculate accelerations of objects. In this picture, we have one force or two forces acting on a hockey puck that moves across a frictionless surface in one-dimensional motion. The mass of the puck is 0.2 kilograms. And there's forces F1 and F2 that are directed along the axis. F1 is to the right with a magnitude of 4 newtons. F2 is to the left with a magnitude of 2 newtons. And we're going to calculate the acceleration of the puck in each of the situations. So looking at this, if I fill in the values, F1 is 4 newtons. So if I'm drawing a free body diagram, that's what they show in picture D. They show the force that's acting on the puck. We have force 1, so we represented the hockey puck as a dot for simplicity, and we draw that force of 4 newtons acting on it. There are also two forces that aren't shown in this picture. I want to include them because they are going to be things that we need. There would also be the weight of the object, but the reason we're not going to worry about it in this problem, the reason that it didn't include it in this problem, since it's moving in one dimension along the x-axis, there is also an upward force of the ground that balances that out. If it's moving in the horizontal direction, the forces in the vertical direction are going to have to balance each other out. And so in this first case, where there's just the 4 Newton force acting on it, I calculate the net force. I have to add all of the individual forces together. Again, the force of the ground and the force of gravity, those add up to equal 0. Those balance out. And so we get that the net force is 4 newtons. Again, the net force is all of the forces added together. But we have to be careful because they're going to be vectors, so that's going to be important. So in this case, the net force is 4 newtons, and Newton's second law says that the net force acting on an object equals its mass times its acceleration. So I get that the net force of 4 newtons equals the mass, 0.2 kilograms, times the acceleration. Or if I solve for the acceleration, I get that the acceleration is 20 meters per second squared to the right. In the second situation, I still have the force of 4 newtons acting to the right, but now there's a force F2. Someone maybe is pushing against the hockey puck. So I have this force to the left of 2 newtons. Again, there would be the force of gravity and the force of the ground pushing up. Those balance each other out. so I don't need to look at those. If it's moving along the x-axis, I'm going to be looking at the forces along the x-axis because the other one's balance. And so doing this, we're going to set it up so that the right is the positive x direction. And so when I calculate my net force in this case, the net force is the force of positive 4 newtons to the right, plus negative 2 newtons, because it's 2 newtons to the left. So that gives a net force that's positive 2 newtons. Overall, the equivalent force is a force of 2 newtons acting to the right. And that net force equals 0.2 kilograms times the acceleration. So setting those equal to each other, I have that 2 newtons equals 0.2 kilograms times the acceleration. Or I get that the acceleration is 10 meters per second squared to the right. Again, if F2 would have been bigger than F1, then I would have had a net force to the left that would have caused the hockey puck to accelerate to the left. So you have to understand how to add vectors together. You're not often going to have them just in one dimension, so you do need to break vectors into components, use vector addition. But when you go through and you calculate the net force, that net force then can be used to calculate the acceleration of the object. And then you could use that acceleration with kinematics if it's a constant acceleration. Or you could go through, it's that acceleration now that affects the motion of the object. The final thing that I'd like to look at briefly is Newton's third law. And his third law is the law of interaction. And this is one that most people have heard. And most people have heard the short version. For every action, there's an equal and opposite reaction. And that's great. It's easy to remember. But most people, even though they can give you that short version, they have no idea what it means. You have to understand in that an action and a reaction, those are referring to forces. So what that says is for every force, there's an equal and opposite force. And that doesn't make things as clear. And so the longer version that's shown on the screen is a little bit better. This is what you should remember for Newton's third law. When one object exerts a force on a second object, the second object exerts a force back on the first object that is exactly equal in magnitude, but exactly opposite in direction. So if I have the Earth and I have the Moon in orbit around the Earth, the thing that holds the Moon in its orbit is the gravitational pull of the Earth on the Moon. What Newton's third law says is that if the Earth pulls on the Moon with a certain size force, then the Moon must pull back on the Earth with exactly the same size force, but in the opposite direction. This would be true no matter what the two objects were. If this was a baseball that was being dropped and it's falling towards the Earth, we know that it falls towards the Earth because the Earth pulls down on it. But what you don't often realize is that as the ball is falling down, it's actually pulling up on the Earth. The reason you don't notice that is because the mass of the Earth is extremely large compared to the mass of the ball. So you have a somewhat small force acting on the ball, but because of its small mass, it has a very noticeable acceleration. You have the same small force acting on the Earth, but because its mass is extremely huge, you get that acceleration is so small that it would be very, very difficult to measure. But it is true that if the Earth pulls on the ball, or the Earth pulls on the Moon, then the ball or the Moon must pull back on the Earth with exactly the same force in exactly the opposite direction. And so what I'd like to close with is this little cartoon that sometimes you see that illustrates some misconceptions with Newton's third law. So there's a horse, and there's a man trying to get the horse to pull his cart. So he says, "Giddy up, pull the cart so we can go along." And then the horse, thinking he understands physics, says, "Well, no, that's not possible. If I pull on the cart pulls back on me. Newton's third law says that the forces are equal and opposite, so they cancel out." And so the farmer is a little bit smarter. He says, "Well, I only care about the forces acting on you. I don't care about the force that you exert on, I only care about the force exerted on the cart. I don't care about the forces on you." And then the horse says, "How can I pull the cart forward when the cart is pulling backwards on me?" And so the explanation to it is the reason that the horse is able to move forward is that he pushes back on the ground. So even though the cart is pulling back on the horse pushes backward on the ground, and so that means that the ground exerts an equal and opposite force forward. That forward force on the horse is bigger than that pull of the cart backwards, and that allows the horse to move forward. And so when you're applying Newton's third law, you need to make sure that you're only looking at forces acting on the object you're looking at, not looking at other forces. These pairs of forces never cancel each other out because they're two separate forces acting on two separate objects. This is something that we'll be studying a lot more, applying to different situations, but I wanted to fully summarize Newton's 3 laws of motion.